I cannot see anyone on my screen.
Okay, it's okay, Sundar.
Yeah, okay. So,
So
well,
good.
everyone. Okay, so Shurudip, you want to go? Or
Please proceed, Sundar. Please proceed.
okay. Okay, so welcome everyone to this 11th episode of weekly seminar on quantum information. And this week we have Yago. Yago is a PhD student at JIC, Autonomous University of Barcelona. And he's doing his PhD regarding these problems around state discrimination, state anti-distinguishability, and related notions. And today we have invited him to talk about some of his works, like semi-definite programming for quantum information problems. And we have requested him to talk about basic stuff at the beginning, and then he will talk about some specific problems. So I hope like every one of us will get something from this talk. And also to Iago, I will say that because there will be questions, and if we cannot finish the whole content of your talk today, we can assign another session, like the next session. You can continue then. Okay. So keeping in mind, you can start. Okay.
Okay. So hello everyone. I will, as some said, start with some basics of first optimization, then semi-definite programming, and why it's important in quantum information. And then I will jump more specifically to the problems that he mentioned on state discrimination and state exclusion. And I won't go that much into the details of the work I've been doing, because I will need to explain some other stuff, because we are working with some structure of the problems that have some symmetries, and I will need to go on group theory, and I think it's out of the scope of this talk. So I'll introduce the basics and what can we do. I will try to go into the details, but not too much, not covering semi-definite programming at least. And let me start on why semi-definite programming is important for quantum information, and that I think is very clear, but it's important to know because a lot of objects in quantum information, like states, measurement, coed matrices of channels, and a lot more, are positive semi-definite matrices. If they are not positive, at least, they are hermetic. And this is one of the things that we need for doing this convex optimization, of semi-definite programming. Then a lot of transformations that we do in quantum information are linear transformations over these objects, like coed matrices or states or measurements. And a lot of the problems that we encounter in quantum information can be written as an SDP problem, like that fulfill the constraints and everything. And I will go into the definition of these constraints and the objects that we need. So for this, it's important to go into semi-definite programming for quantum information. And I will cover at the end, hopefully at the end, if I can do it on time, what kind of topics can we expect to do as a semi-definite program inside quantum information science. But first, what is optimization? So imagine that you have a set of options, and each of them has associated some cost of choosing this option. That here I write it as the options X and the cost of each of them as F. And I will stick to these colors all the session to make it a little bit more clear, and you'll see that it gets complicated very fast, or at least a lot of colors appear. So everything that we need to optimize that we can choose will be written in this blue, and the costs of the associated problem will be in this purple. Okay. And given this set of options and the cost associated with them, Our task is to choose which option minimizes or maximizes the cost. But in here, it minimizes. Always that you need to maximize, you can write a minus, for example, in front of it, and you can convert it to a minimization problem. So it doesn't matter if I talk about minimization or maximization, you can always convert it to the other kind of optimization. But in general, we don't have a set of options that it's finite. We can encounter some examples, some easy examples in which the set of options is infinite, or a field, or a vector space, or something. For example, the set of real numbers that minimize some sort of a function, or something in a vector space that minimizes also a function. Okay. More formally, an optimization problem consists on a triple, that is the variable and the space where it's contained, this variable, a function that we need to minimize, that is usually called the objective function that we want, the cost associated with the choice of the variable that we do, and map on this variable that are the constraints that we will impose to that we want our variable to fulfill. We have two kinds. One of them is the quality constraint, and the other are inequality constraints. So under these triples, we can define a set which we call the feasible set, that are all the x's, all the variables that fulfill the constraint relations. Okay, and we say that when we have no variable that fulfill these constraints, the problem is called unfeasible. Okay. So a simple example would be, for example, what is the vector in the first quadrant of a unit square? And here you can see the figure that has the greatest overlap, sorry, with this vector. So our variable lives in R squared, and our objective function is just taking the overlap with our variable with this vector that we have in the problem. And what are the constraints? Well, the constraints are the ones that make that our vector is in the first quadrant of the unit square. What is this? That the first component is greater than 0, the second component is also greater than 0, and then this the first and second components also are less or equal than 1. And we can write our maximization problem in this case as this form. I mean, you will see this form all over the lecture, the seminar, which is, okay, maximize some x on the set that we want to, over the set we want to maximize, such that maximizes this overlap with the overlap with the vector we wanted to optimize over, such that fulfills all these 4 inequality constraints we mentioned before. And we can see easily that the best option is just this vector. Okay, we know we will go much into more details when we go to semi-definite programming. For semi-definite programming, the form is not like the one we just saw. It will optimize over an Hermitian space, in here an Hermitian variable, such that the Hermitian conjugate, the complex conjugate, the transpose complex conjugate, sorry, is equal to the operator, and the objective function is taken of the form of trace of some operator A with our variable x. And the set of constraints that we want our problem to fulfill are linear maps over these operators that preserve, and this is important, that preserve hermeticity. Okay, so the usual form, which is not called the standard has another form, is the minimization over X of the trace with our operator A, subject to some conditions, some conditions over these linear maps that are hermeticity preserving. We can have two kinds.
Yago, I have a
Yes,
question.
sure.
So does this A operator has to be Hermitian always? Like, is it important somehow? Like, is it necessary for A to be Hermitian?
There are some cases in which you don't need, but in most of the cases, it's needed to be Hermitian. You can relax some you can relax some assumptions on the hermeticity of the operator, but and you can convert it to an SDP problem. But yes, you need A to be an Hermitian operator, at least as far as I know.
So you say that, like, for all practical purposes or like problems in quantum information, we will usually have A to be Hermitian. Like,
yeah, I'm not aware of problems that are not Hermitian.
Right.
This scenario, but it could be that there are, and you make some relaxations, or you play a little bit with your operators and make it Hermitian, with some tricks, let's say. But as far as I know, and the problems I present in this session are all Hermitian, all the A's.
Okay. Thank you.
Yes. No problem.
I have just one confusion here. So if it is not Hermitian, why it would not work?
Sorry?
So
Come again?
I'm asking if A does not satisfy the hermeticity property, why it would not work? I mean, is there any particular reason why it would not work?
It does not work for some technicalities that we'll see afterwards, but for you want to preserve the hermeticity to know how the product, or at least the trace of the product, is positive or negative or undefined. There are some cases in which you impose this when working on the dual, and your problem easier to solve.
Hello.
Okay, thank you.
Yes.
Am I audible?
Yes, you are.
If A is not Hermitian, then the objective function may not be real, right?
It could be. That's, but sometimes it would be if it is not Hermitian. But if you want to impose that it's real, or for granted, it should be Hermitian. But there are some cases in which still the objective function might be real.
Real, okay. But if the objective function is not real, there is no point of minimizing. I mean, it have to be
no,
real.
You cannot minimize over the complex numbers, of course.
Okay.
Achha, I have one question.
Yes.
Is this this function that you are calling as the objective function, that is of the form of trace of AX? So basically, this is the inner product in the space of all operators. Like you have trace of A dagger B. So you are actually always optimal. You're trying to optimize a function which is in the form of a trace of AX. That means an inner product.
Yes.
Yeah, so that means you are saying that every time this objective function will be of this form, like the Hilbert-Schmidt inner product, that is trace of AX.
Yes.
Okay,
sorry, I don't get the question.
No, I mean to say that the objective function that you are writing, it is of trace of AX, is of this form.
Yes.
Yes, so my question is that this trace of AX is basically the Hilbert-Schmidt inner product between A and X.
That's correct, yes.
Yes, so will the objective function always be of this particular form, that it is an inner product between two operators A and X? Or
Yes.
It can be another function also?
No, it's of this form. And you can convert always, for example, you can have a sum of terms with trace AX plus minus whatever trace by, and you could still convert it to this simple form of trace A and X.
Okay.
It always has this form, at least on the primal. We will see what the primal is.
Okay, fine. Thank you.
But yeah, yes, it always has this form. And you can transform all semi-definite programming in what is called the standard form, that is trace of A times I product with X, the Hilbert inner product.
Okay.
I'm a little bit lost. So the last thing I said, sorry, is that our programs are always of this form, that we want to minimize the objective function over some space of our variable, subject to some constraints that have to be fulfilled. Okay. Every semi-definite program has an alternative formulation, that is called the dual program. Sorry, and it can be defined previously from the triple that we had previously, but I find it more instructive to obtain the dual version through what is called the Lagrangian of the problem. And what we do is we associate a Lagrange multiplier, to each of the constraints. So in some sort, we are introducing a penalty for each of the constraints that is not fulfilled. And these Lagrange multipliers are what are called the dual variables that we'll see in the dual version of our semi-definite program. So if we start with a primal, we can convert this primal program into a dual, and that we are maximizing over other different spaces, and we are minimizing. We are optimizing that's subject to the fulfillment of or some other constraints. And to do it, let me go into the derivation of it. There is given the maximization of the trace, the inner product of A with X, subject to some constraints are fulfilled. We construct the Lagrangian with the value that we want for our problem. Then we introduce a Lagrange multiplier, a dual variable yi, for the constraint, for the first kind of constraints, and we sum over all given constraints that have to be fulfilled. And we sum another term, introducing another Lagrange multiplier, in this case, set j, for each of the inequalities that we want to fulfill. Okay. Then, for deriving the standard form.
Iago?
Yes. So
this yi and zj, these are like real numbers, or they could be anything, any operator.
They are operators in general, because in here this form of the constraints is a linear map over the operators that have to be equal or less or equal than some other operators. It could be real numbers. It could be. It depends always on the map, but in general are operators.
Okay.
Okay, so to obtain the dual, we group the primal variables. In this case, we only have one, dx, and we group it with some expression. And then we have the rest of the terms that do not depend on the primal variables. And this part over here is the objective dual function. Okay, but we need more things. First, notice here the dagger on the maps. And this is what is called the dual map, or the adjoint maps of our primal maps. And they are defined uniquely with this relation. And you'll see that it's easier to find that it appears. So you don't need to find always the dual map. You can construct it via the Lagrangian.
Okay,
And we'll see it with with the state discrimination problems that we'll see that it's easier to write them than this complicated form. Yes, sorry, tell me.
So for every SDP, there will always exist a dual of that SDP, right?
Mm-hmm. That's correct. Yes.
Okay. So this statement is something like a theorem, or it's just a very trivial statement?
And there it exists. I don't know if it is a theorem itself, but you can define the primal and the dual from the triple that I mentioned before. A space,
is this
cost function, and the constraints.
Okay, so is this actually come from the fact that the solution of the SDP is always a convex set? So then it will always form a dual SDP.
Yes.
Maybe. Okay.
But this form part, SDP is a specific scenario of convex optimization. If you have no convex sets or convex functions to optimize, you cannot ensure that a dual exists.
Okay.
But I thought that this was a little bit more mathematically driven for the. I will not prove everything. I will derive things that I want to derive for my problem. So it's kind of specific in this in this sense. I will not prove every theorem or I will not go much into the detail of defining mathematically what these sets are and the convexity of the set of the feasible set and everything. I will try to stick to the at least important for me things. But yeah, you need convex optimization problem to ensure duality, as far as I know. I think so, but don't trust me on this. But I think you need convexity. So we following the the thing I was saying, we have this thing that doesn't depend on the primary variables, and like we call the objective dual function, and we have this object over here that it's taking the trace of our primal variable with some expression on the objective of the objective function we wanted in the primal, and some maps over the dual variables. So we want to make this program, the dual, independent on the that does not depend on the primal variable x. So we want first that this expression over here is equal to 0, and this will form the first constraint of the dual problem. And also we want that the Lagrangian is always greater or equal than the objective function for every operator x on the primal form. So for that, as Cj minus gamma j of x, this constraint over here is always positive, we impose that our dual variable set j has to be positive also. And this defines the constraints of our dual program. Okay. So let me go one previous slide. We have the primal form, and we can derive the dual SDP that will be helpful in the future. Yes. Tell me.
So can you hear me?
Yes, I can hear you.
Yeah, I like to understand the motivation of dual SDP. Like the motivation of SDP is to solve a linear optimization. So is it so that sometimes that primal optimization is harder than the dual optimization? Is it that's why we are going?
It depends on if you have a minimization or a maximization. But in this scenario that I have a maximization, okay, I want the dual to be greater than the primal.
So our motivation is to optimize a linear linear function. Okay, so why we are going to that dual domain?
You will see in the next slide, but you can relate things of between the primal and the dual, and sometimes it's easier to convert the primal into a dual SDP to solve the dual instead of solving the primal, subject to some conditions that are fulfilled by your problem. Maybe it's easier to solve the dual and you will still get a bound or the same exact value as solving the primal. Sometimes it's easier. And in here, it seems more complicated, but you will see that for some scenarios, it's actually easier, the dual, than the primal.
Oh, thanks.
Also, because when you are doing numerics, you'll see that the primal and the dual have a relation between the values of the solution of these problems. And the computer, what they are doing is solving the primal and the dual at the same time and minimizing the gap between them in order to give you a solution. So it's also, let's say, an application of the duality that is important. But for me, it's more related to how to solve analytically a program.
Oh yeah,
a maximization problem.
Hello.
Yes.
Yes, I had another question. Like when you are optimizing this objective function, so the set on which you are optimizing, shouldn't that be a compact set? Shouldn't that be a compact set? Otherwise, you will not get the extremum in that set.
It would be a convex.
Yes,
which is compact and closed. Yes.
Yes, it has to be
no,
closed.
compact is closed already. Yes.
Yes, that is what I'm saying, that it should be closed as well as bounded.
Not really.
That if you are talking about it has to be convex first of all. Secondly, it has to be then bounded in case of finite dimensional spaces.
Yeah, but you can define, well, the set has to be bounded. Sorry, I got confused. But the objective function doesn't need to be. But yes, the set has to be compact in this sense. Close and
yes. I'm talking about the set. I'm not talking about the objective function. Yes. That this restriction should be there. Otherwise, the extremum is not possible within that set.
It could still be possible if not bounded. For example, for the Hermitian operators or the semi-definite positive matrices is not bounded.
No, but why are you saying that they are not bounded?
How do you define the boundaries? The extremal point.
What I'm saying is bounded. I mean, I'm talking about the bounded. Or if you take a norm of this observables x, so that will be bounded by some number. If it is not closed bounded, that means what I'm saying in finite dimensional spaces. I'm talking about finite dimensional spaces. So the observables that you are taking, that is this x.
Yes.
Yes. So what I'm saying is that this set should be a bounded set.
No.
Not necessarily.
For example, if you don't need the constraints and you are maximizing over the positive operators of, let's say, the projector onto the zero in quantum. Let me write a slide. So if you are maximizing x of trade 0. Sorry, I think I lost the connection. Can you hear me now?
Yes, I can hear you.
Okay. So if you are maximizing over set is pos, you have no, it is not abundant.
No, but see, I think
that they are optimizing over.
No, miscommunication, because by bounded, what I'm trying to say is that if you define a norm, so norm of x for any x belonging to that set will be bounded by some number. That is what I'm saying by bounded.
I cannot think on a norm that bounds this set, because I can make X some value A, and if I take the trace norm or some other norm, this will be infinite.
The trace norm is infinite. How can you say the trace norm is infinite for this case?
Sorry, come again?
Like how the trace norm is infinite in this particular case?
Well, the set norm is A, right?
Huh?
And I can make A as large as I want.
Okay, Acha. So you are saying that there is no restriction on this A that you are taking?
No.
Okay.
But
okay.
in here, this problem will be the dual, of this problem will be unfeasible, because I cannot get something that is greater than infinity.
Yes, yes. That is actually what I'm trying to say.
So this problem has no solution.
Yes, so that means that is what I'm saying.
But
that
it doesn't matter. I mean, you wouldn't obtain a value from the program.
Okay.
But still is an SDP form.
So what are the restrictions?
The problem is that
that means, so what are the restrictions that you want on this set?
To be convex.
You just want it to be convex.
Mm-hmm.
Okay, fine.
And also the set, you can restrict it with the constraints, and you can define what is the feasible set. Okay. And this restriction, when you are taking into account the constraints, you need that the feasible set, is bounded. Now, yes.
Okay, fine. Okay.
And you have two options, or you have a bounded set, or you have no set at all.
Okay, fine.
And this you call it infeasible. But in principle, you don't need to impose that is bounded.
Okay.
The only problem that you have is sometimes you wouldn't obtain a value. If you make the constraints, you will obtain a bounded set.
Okay, please continue.
So was this derivation, which I think it's important, clear on how do we go through the from the primal to the dual, and why are we making these constraints? Someone? Was it clear?
I have one question. So from the CJ difference gamma j x greater than equal to 0, that is the second constraint in the primal problem.
Yes.
So from that you obtain a bound, or like zj greater than equal to 0. So that is a constraint on the dual problem. But also you have the other constraint in the primal problem. So does not that give you another constraint in the dual problem on yj or something?
This one.
Yeah.
It gives you this one.
No,
but in
I'm
here
talking about this phi ix equal to bi.
You will have another constraint that I haven't written. That is that y is Hermitian.
Okay.
Because in here, as you have an equality, okay, if it is not fulfilled, it can be positive or negative.
Right.
And you don't need y to be positive, because sometimes you can minimize by not fulfilling this inequality, but by some negative operator, and you could minimize the Lagrangian. And we don't want to be less than the objective function of the primal.
Okay.
But you have this constraint in here.
Right. Okay.
But in principle, you are always using Hermitian operators.
Okay. So we are
if it
optimizing
is,
over. Okay. For Yj, Yi, we are optimizing over Hermitian operators, and Zj
yes.
is any positive operator.
Sorry, a semi-definite positive, a positive semi-definite operator. Sorry.
Yes, positive semi-definite operators. Okay.
On some space, it does not need to be Y and Z belonging to the same space.
The same space.
At
Okay.
all.
Of course.
Okay. It doesn't need to be like this.
Okay.
With this definition, what we can show is that we have what is called weak duality. And this weak duality is just this thing I have written below, that here alpha is the value, the optimal value of the primal program, and beta, and beta here is the optimal value of the dual problem. And for this scenario in which we have a maximization, yes?
Hi, I had a question. Can you go back to the previous slide? I think I have a little problem with the constraints here. So since we are okay with taking the trace to be negative, so in the second constraint, I understand why.
Sorry, which
so in the Lagrangian, you want to minimize, right? So here I have three different these expressions: trace of AX, then the next is summation I trace over YI, and then next is summation over J trace over ZJ, like that.
Yes.
So I understand your second constraint where you want Cj minus gamma J to be greater than 0. That is coming from the primal. That is coming from the primal. But why do you want Zj to be greater than 0 there?
Because what we want to do is minimize the Lagrangian, but this Lagrangian has to be always greater than the objective function of the primal, in order to define weak duality, which is the next slide. So the constraints appear because you add some Lagrange multipliers to the objective function related to the constraints, but you want always this Lagrangian to be greater than the objective function of the primal. So you want this thing and this thing to be positive.
But I think you just said 2 minutes back that yi can give me negative values.
No, we want to make it Hermitian, because this, if you don't fulfill this equality, it could give you some operator that might be negative. So if you restrict yourself to y only positive, you will have here some trace that is negative, and therefore it could subtract from the primal objective function and make the Lagrangian less than the objective function, which is a thing that we don't want.
Okay.
So for this thing, in order to compensate that the equality can be
and make it negative,
violated in both directions, negative or positive, we are making that our Lagrange or our Lagrange multiplier or dual variable belongs to the is Hermitian, not only positive.
But if it is positive, that means it is Hermitian, right?
Yes, but it could be Hermitian and not positive, nor negative. That's why.
Okay, you can carry on.
So, yeah, with weak duality, this is the relation of the optimal values of the primal and the dual. And we have that for any feasible solution of the primal, we have that because it's feasible, the constraints will be fulfilled, and then the Lagrangian will be greater or equal than the objective function of the primal, the output value of the program. Okay. So if we convert this optimal value, okay, with the constraints that we have, we will obtain a bound that is just the output of the dual program, and this relation gives you a lower bound for the dual program and gives you a upper bound for the primal program, and this will lead to some results of how we can solve analytically, or at least how can we be sure about that some program is feasible or not. Okay, so this thing is something that holds by construction of what we did with the program. But a much stronger condition is strong duality. In here, we have that both values are equal, and that's why, let's say, I want the dual SDP. That was a previous question, because sometimes I want to solve the dual problem that it's easier sometimes only than the primal problem. And if I know that strong duality holds, I will obtain the same value as the maximization of the primal problem that might be super difficult by optimizing only the dual program. And I will obtain the same value. That's why I want it. It's something that it holds for some problems. It's not something that I can impose it. So it's something that I want to check or not in order to solve through the dual a problem. And for example, in state discrimination, it happens that a strong duality holds. Okay. And we need to check that some conditions hold. That is that the feasible set of the primal is non-empty. That is that it's not that there are some operators that are feasible under these constraints, and we want to check that it's strictly feasible. What it is that okay, the equality constraints, stay the same, but the inequality constraints are strict inequalities instead of being less or equal than CJ. And the solution of the primal is finite. Okay, so the optimization program is not unbounded. What are the conditions? What these are called the Slater conditions. That okay, if the primal SDP is strictly feasible unbounded, then strong duality holds, and the value of the primal and the dual coincide. The same discussion can be done with the dual. The dual has its own dual, which is the primal SDP. So if it is feasible unbounded, then strong duality holds. And again, the values of both programs coincide. And the third, which is of course a direct relation, is that if both the primal and the dual SDP are strictly feasible, then strong duality holds. And why is that? Because weak duality is something that it's always true. Weak duality. But strong duality is something that we need to check. And for some programs, it is true, it holds, and for some other programs, it doesn't hold. And in here, because the primal is strictly feasible and the dual is also strictly feasible, we have a lower bound, for example, for the dual. So the dual is strictly feasible and bounded by the solution of the primal, by weak duality. And then we have a strong duality that holds. Okay? And there are some scenarios also in quantum information that strong duality doesn't hold. Okay, but for the things I've been working on, it holds. Okay.
Hi.
So, yes.
Hi. Yeah. Can you please explain what is strictly feasible? Like
strictly feasible is what I said before, that the constraints, okay, we had before we had that these constraints were less or equal.
Yes.
And now, if it is strictly feasible, it means that the inequalities are strict and they are fulfilled by some operator X.
Oh yeah, only inequality is fulfilled, not the equality.
The equality has to be fulfilled always. And now the inequality, we convert it to a strict inequality. And if this strict inequality is fulfilled, then it's strictly feasible.
Oh yeah.
But the qualities remain the same.
Yeah, yeah.
So I want to talk now about complementary slackness, which I use it as a tool because it gives me a lot of information about the form of the dual or the primal variables. And let me explain briefly. That is that it comes from strong duality. So if we remember from the Lagrangian, if we substitute every operator for the optimum, let's see here that it has the star for the optimum, denoting the optimum, the optimal solution, sorry. We want the optimal variable is feasible apart from being optimal. So this trace over here vanishes. And the only way that so this thing is equal to 0. And from here, we have that this thing is the trace, the second term of trace with the Lagrange multipliers of set J, are positive because we constructed like this. And the only way that the Lagrangian is equal to alpha, the optimal value of the primal, is that this thing that by construction was positive is equal to 0. And I don't know if I have another slide. Yes. And so we want that this sum over here is equal to 0. And because it's positive, each of the elements of the sum has to be 0. And it's easy to see that if you have two positive operators and that the trace of these two positive operators, the inner product of them, is 0, the only thing that can happen, is that the product of these matrices is equal to 0, is the 0 matrix. So they commute and they diagonalize in the same basis. If we denote by pi j as the space where these, let me read. No, sorry. So the question was that for strong duality to hold, does the whole set of feasible points has to be strictly feasible? No. When you have one feasible solution that is strictly feasible, that's enough. The optimum does not need to be, or the whole set does not need to be strictly feasible. But some operator must be strictly feasible. So the strictly feasible set must be non-empty for a strong duality to hold. Okay. Sorry, when I was if we denote by pi j the space where this object has support, then the support of Z is contained on the orthogonal space of this operator. And this gives us relevant information about the dual variables. Okay, a lot of information, because you can construct these variables, these dual variables, by, let's say, by hand, in order to fulfill the dual variable. And if you check that the primal and the dual have the same solution, then you have obtained the solution. And you can solve the optimization problem by just checking a point, 2 points, one from the primal and one from the dual. Okay. So let's go to a simple example that maybe was too abstract. And the example is, okay, let's find the maximum eigenvalue of a matrix A. Okay, so what is the problem that we have? We want to maximize over some operator X, and we want to maximize the inner product of A with X. And we want, what do we want X to fulfill? We want to be subject to that the trace of our operator is equal to 1, and that our object is equal to 0, greater or equal than 0. Why do we want to be 1? Because we are projecting onto the direction of the eigenvector associated to the highest eigenvalue. And why do we want to be greater, positive, semi-definite positive, this matrix? Because if not, we could minimize, we can sum, for example, if you have a matrix A that has negative eigenvalues, we could subtract from the trace, but summing on the inner product. And we can convert this primal problem into the dual by the Lagrangian. So we have the objective function, and then we associate a Lagrange multiplier that is in this case t, and t is a real number, multiplied by the condition that has to be fulfilled, and we sum the trace, the inner product of x, our primal variable, with some Lagrange operator that has to be positive. So we group up all the things with the primal variables, and we have an expression, and then t that comes along from this object here. So, I'm sorry, here I forgot to say that it is positive. So we have this constraint must be fulfilled because the dual program cannot depend on the primal variable, and this thing that is free. So we want to minimize over t, the real numbers, such subject to that this constraint is fulfilled. And why did I put it an inequality when I told you before that this thing was an equality? Because I'm considering, I'm using the set variable that is positive to say that z is equal to this operator. Let me write it because maybe I'm doing things not very clear. That z is equal to, sorry, t, the identity minus a. If this thing is fulfilled and z is greater than 0, it implies that t identity minus a is also greater than 0. Okay, so we can erase this condition, and we only need this constraint to be fulfilled. Okay, that was clear? Was it?
Yes, for me it is clear. Yes.
Okay, we can do something a little bit more sophisticated that is not, let's say, an SDP. If I ask you to compute via SDP the fourth largest eigenvalue of a matrix, that cannot be done by an SDP. But we can play with SDP to find this value at the end. So we can think of joining, let's say, two SDPs in order to obtain this value. If we consider the sum of the four, let's say, largest eigenvalues, and then we subtract the value of the r minus 1, the sum of r minus 1 largest eigenvalues, we are left with the rth eigenvalue, largest eigenvalue of the matrix. So, okay, we can compute the sum of the first r eigenvalues of the matrix A. Okay, and this is an SDP, and it's very similar to the previous one. That is, okay, maximize over the operators x, such that maximize the trace of a x, subject to, okay, now because there are different eigenvalues, sorry, we want to compute r different eigenvalues, we want the trace of x to be r. Again, we want x to be positive semi-definite, sorry, and we have to add one extra constraint, that x is less or equal than the identity. Why? Because if not, we could put r on the first entry of the matrix and just compute r times the largest eigenvalue. But with this constraint, we can split, let's say, the operator x into the different eigenvectors of the matrix A with the r first eigenvalues. So again, we construct the Lagrangian, that is the objective function. Then this t.
Then should it not be strictly less than identity, or why do you allow also equal to identity?
Because if I want to compute all the eigenvalues, I need to be equal to the identity.
Okay. If r
is equal to n.
Okay,
yes.
okay.
But if I this way, I don't do it. But in any case, sorry, because imagine that you have this matrix, let's say 1 0 0 0. Okay, this is not less than the identity.
No, it is.
Okay. No, it is not, because you have 0 minus 1 here, and 0 is not less than 0.
No. The first one is so on the left hand side you have written like 1 0 0 0. So this is a projector on some space, yes, which is like the first one. Then and if you add with it like another projector which is like 0 0 0 1, then it will add up to identity, right?
Yes.
So it is, I mean, but that other operator which is 0 0 0 1, so this is a positive operator. So then
yes, but wait 1 second.
How can it be not less than?
Because it is defined differently. So when you have A is greater or equal than B,
yes,
this thing is that A minus B
is greater or equal to 0.
Is greater than 0. Okay.
Yes.
So
of course,
the singular values of I minus B, all of them are greater than 0.
Positive semi-definite. Okay, of course. Yes.
But in this example that I show you, we want that the identity minus this projector, for example, okay, is you told me that this thing we want it to be greater than 0. Okay. When you don't fulfill all the possible eigenvalues, all the space, no? But this thing is not true, because you have 0, 1, and the singular values of these things are 0 and 1, and 0 is not greater than 0. It's greater or equal.
It's equal. Okay, of course.
So indeed, not only when you don't cover the whole space, but you need to be less or equal.
Okay.
It doesn't matter, because at the end, the limit of this maximization will be the supremum of the SDP, and even though it's not achievable, you can still work with the supremum and not the optimal value. But in any case, it's better if we do it from the beginning correctly. So no, you need the less or equal then.
Okay.
So why do you take the trace of x to be r?
Sorry, come again. I didn't hear you.
Why is that trace of x is r in the constraint?
Trace of x.
equal to R? Should not it be
Because
1?
we are computing R different eigenvalues. Yes? Or
yeah, so X operator is like the projector over the first
is the projector
R eigenvectors, right? Eigenspace.
That's
like,
it.
Yeah.
The solution at the end of this problem would be that X is equal to the sum of 1, I equal to 1, up to R of 1, because it's the projector, of BI, where BI is just the eigenvalues, the eigenvectors, sorry, of A.
Yes.
Yeah.
And that's why if we trace here, X is equal to R. That's why it's equal to R, our trace and this condition.
Oh, thank you.
Okay. Then, okay, so from the first constraint, from the first from the first constraint, we have this term in which T is real, and then we add another Lagrangian multiplier, sorry, that would be positive, and then another one which will be also positive. Okay, this way. Then group up everything with the primal variables, and we have an expression that has to be equal to 0. Okay, so this is the first constraint. And then, our dual problem will be this expression that does not depend on the primal variables. So this is minimizing the trace of y, and we added t over t real and y in principle at the beginning Hermitian, such that this constraint is fulfilled, okay, and y is greater or equal than 0. Why y has to be greater or equal than 0? Because identity minus x is positive. So we add a penalty, a positive penalty. Okay, and why this condition has to be fulfilled? Because if we solve for z, okay, we end up with this constraint over here. Okay, and if we do it for r and r minus 1 via 2 SDPs, we can find the r largest eigenvalue, which is not an SDP problem from the beginning. We needed 2 instead of 1. Okay, so this is a simple example, but I think it illustrates quite well how via SDPs we can solve non-SDP problems and why it's useful. Right?
Yeah.
Good, up to here?
Yes, yeah. Okay, maybe I think, what do you think? This is the right time to stop for this session, and then maybe next week we can continue, or you will just want to add something?
No, probably yes, because now is the time when I describe a little bit how do I use SDP and move completely to state discrimination, state exclusion. So probably it's a good time.
Yeah. Anyway,
let me probably go on to the last slide, and I will start from there next week, which is how I use SDP for getting the analytic solution. Because of course you can do it from via numerically, okay, and you will obtain some insights on your problem and that help you to solve it afterwards. But you can also solve things analytically. So first of all, okay, write your problem in an SDP form, which is sometimes not trivial. And then construct the Lagrangian and the dual, okay, and you have both things, and check that the strong duality holds. Okay, if a strong duality holds, this is crucial to solve it, because you can get information, first of all, from complementary slackness in order to construct, let's say, your Lagrange multiplier, your dual variables, with this information, this new information, so you can restrict yourself to a smaller space than the space where these operators that we obtain from complementary slackness live, and construct these dual variables with this new information. Then how do you get the solution at the end? Then you find, with a, let's say, educated guess, you find the optimal of the primal, or not. Let's say you find a feasible point on the primal and a feasible point on the dual. And if you construct them well, if they have the same value, you have found the optimal solution. Which is kind of a joke, but this protocol can be said as a joke as, okay, look very, very hard to the problem that you have, think very, very hard, and then you get the solution at the end. But with these pieces of information that you have, you can do things analytically and not only numerically. And we will see for quantum state discrimination. And then that was it. And next time I'll go to state discrimination, which I promise is way clearer because the problems are fixed and you can construct everything and you can derive everything. That was it.
Thanks, Santiago, for the nice talk. It's still clear for many of us who doesn't know SDP beforehand. At least I got something on it. So any more questions? Maybe last 1-2 questions.
Thank you.
Okay, since there is no more questions for today, so see you next week, and thanks again for nice presentation. Yeah, bye.
Thank you. Thank you.
Yes, thanks. Bye.